In this video, I will talk about ligand substitution reactions, and I will also mainly talk about the oxidative additions. So, what is the reaction? I can try to write it. So, for instance, this is a ligand substitution reaction. This ligand substituted to the metal center, and another ligand, this one, L prime, and eliminated from the metal center. So this is a ligand substitution reaction. And there are two main reaction mechanisms. The first one is associative, and the other one is dissociative. So in associative mechanism, the complex reacts with the ligand first, and this process is pretty slow. This is a slow process. And then this product gives the ligand, which is the L prime. This L prime ligand leaves from the complex, and this is the fast process. In dissociative mechanism, first the ligand leaves, so this ligand leaves from the metal center, and this is actually an equilibrium reaction, so back and forth reaction, and this is slow. And then the other ligand, L double prime, attacks to the metal center, and this product occurs. So in any case, we will obtain the same product, but reaction mechanism is different. So the first reaction, or the associative reaction mechanism, is preferred by the 16 electron complexes, and the dissociative mechanism is preferred by the 18 electron complexes. The reason is that the metal center cannot take the more electrons, therefore 18 electron complexes prefer to dissociative reaction mechanism. And our main topic today is oxidative addition reactions. So I want to continue with the oxidative additions. And oxidative addition reactions involves the attachment of two groups to the metal complex with relatively low oxidation state. And oxidation state of metal centers increases due to the oxidative additions. And I want to write the reaction mechanism. So we have a ligand, we have a metal, and this product, or this chemical XY, can be added to the metal center. So this is the oxidative addition, and the reverse of it actually reductive elimination. So this is the reductive elimination, which is the inverse of the oxidative addition. And the product is something like this. So the most common reaction is Grignard reagent synthesis. For instance, we have this kind of chemical, which is maybe I can write something like this. We have this one, a phenyl group with bromine, and we have a magnesium metal, and if we heat it in ether, an oxidative addition occurs. Magnesium becomes +2 charge, oxidation state, and this will be the product. So this is a very common reaction, and it is also very useful for the organic chemistry. So this product is very useful, as you know, and it is called as Grignard reagent. And oxidative additions typically occur and oxidative additions occurs on 16 electron complexes. For instance, we can make another example. So hydrogen, for instance, can be attached to this complex, and this complex can become something like this. And we can count the electron numbers. For the first complex, for this one, by the way, this has a plus charge, and as you know, iridium 0 is a D9 system. We have 2 CO, or we have 3 CO ligands. We have 3 CO ligands, so 3 times 2, 6 electrons comes from the CO. We have 2 ligands, so we have 4 electrons from here, and these ligands has -2 charge, so that iridium should be +3 charge, since our complex is +1 charged here. And iridium 3+ in our case has 6 electrons. So this complex is 18 electron complex, right? I just add them up, and this is 16 electron complex. After the addition of the hydrogen, and by the way, there is an elimination of the CO here, oxidation state of the iridium changed. So this is one of the most important part of it, and therefore this is a good example for the oxidative addition. And the other common one is the Vaska's complex. It is again an iridium complex, and I will write the complex. It is something like this. We have CO, PPH3, and we can add, for instance, HX, and X is the chlorine, bromine, or the halogen atom. So it is a trans addition, and this complex can occur. Same complex can react with hydrogen and oxygen. I can write the product and you can check it from the book also. Hydrogen, hydrogen. So hydrogen in the this form, and oxygen can be added. And these are the main products. So I want to talk about the concerted addition. This is another important part. For instance, we have a iridium metal center, and it will interact with the hydrogen. So we have a hydrogen, and the orbitals of the iridium is not empty, of course, and hydrogen can be added with this kind of mechanism. So electrons on the bond, hydrogen bond, can interact with the metal center, and the electrons on the metal can make a bond with the hydrogen. So this is a concerted additions, and this mechanism is also valid for carbon-carbon and sulfur-sulfur bond activations. So for instance, you have this kind of complex, metal 3, platinum. So this is a 16 electron complex, by the way. So this is a 16 electron complex, and this is a good example for the carbon-carbon bond activation, since platinum metal center will interact with the this one, but before, actually 1 second, and there will be a reductive elimination. So platinum then our bond, this bond, triple bond, will interact with the platinum center. Maybe I can write something like this. And there are also electrons on the platinum center. Therefore, these two will be interact. And this product will occur. So this is the final product, and it is a good example for the carbon-carbon bond activation. By the way, why one of the ligands lived? Since p-methyl-3 is a crowded ligand. And if you look at the platinum has 0 oxidation state here, and it is a 16 electron complex. But here, platinum plus 2 oxidation state, it is a D8 system, and at the end of the reaction we still have 16 electrons. If you want, you can count. The other reaction mechanism is electrophilic addition. So we have, for instance, iridium center, and this complex iridium plus, therefore it is a D8 complex. And for instance, we have another molecule, and this is a very good example, like organic chemistry reaction. Bromine is a good leaving group, it will leave. So this is the first step. And plus charge. After the reaction, there will be Br minus signs inside the solution, of course, and this can react with the iridium center since it has so many electrons, and it can attack to the metal center, and at the end we can obtain our final product. So in this case, so if you look at the product, this one, iridium has plus 3 oxidation state, so it is a D6 complex right now, and it has 16 electrons. So after the reaction, iridium oxidation state increased by 2, and also electron number was changed, since this is a 16 electron, but this is 18 electron complex. So main difference between consorted addition and electrophilic addition are the isomerism on the product. Consorted addition generally causes to occur cis product, but electrophilic addition causes to occur trans product. And if you look at our example, this one, we have a trans product, since this is a electrophilic addition. But if you look at the consorted addition, we have a cis product, right? This is a cis product. So consider this kind of molecule. I want to little talk about the mechanism. So this mechanism part might be important. We have a complex, and for instance we have a CH3 group, okay, and we want to add RH, so this is a carbon hydrogen bond. So firstly, the metal center can interact with the bond, this bond, and oxidative addition can occur. It can interact with the molecule, and this is our transition state. So this is a transition state, and we have CH3 of course. And then after the transition state, what can happen is that we will create bonds, our hydrogen and CH3, and after this reaction CH3 can leave, or this CH3 can leave, and it is also a reductive elimination. I didn't mention about the reductive elimination, but basically it is inverse of the oxidative addition, and this product can occur. The other way, so I will write the second way by using purple. The metal center directly interacts with the ligand and our transition state occurs. And after the transition state, so this is our transition state, CH3 leaves and R and hydrogen sticks to the metal center. So this is possible for D0 complexes. So this purple one, purple reaction mechanism, is possible for D0 complexes. Since this mechanism does not require change in oxidation state of the metal center, therefore it is more possible for the D0 complexes. And we can maybe write the interaction or interactions. For instance, this is the case, and metal center has a D sigma bond. So this is a D sigma bond. We have a carbon or the CH bond. So this is a basically CH bond, and this is our hydrogen. By the way, we have a phase of course for the metal center, and an interaction can occur between metal to ligand. So this is basically sigma CH bond, and I want to also write the sigma star of this bond. We can write it very easily. So we have a carbon center, the phase will change, and this is the sigma star interaction, and again we have a metal bond, and this is d pi, and this is the metal center, and interaction can occur between the d pi to sigma star bond of the CH bond. So this is the important thing for the carbon hydrogen bond activation. I hope this video was helpful for you, and thank you for your attention.